In this video we're going to look at inference on means. We start by looking back at sampling distribution of means, which was the probability idea that led to us being able to do inference on means. So we know that sample means are distributed normally with the true mean in the middle, and this is our standard deviation because we would know the population standard deviation. This leads to inference. We can do confidence intervals, hypothesis tests, but usually we are not going to know the population standard deviation. We are going to have to use the sample standard deviation as an estimate of sigma, the population parameter. Because of that, we have the standard error of the means and not the standard deviation of the means. And because of that, we're going to be typically using t-distributions, which work a lot like normal distributions. So let's suppose we're looking at students who are using social media. We're not going to concern ourselves with students using asocial media because we don't care, because quite frankly, they don't care about us. But anyways, we're looking at students using social media and how much minutes per day. Suppose the distribution is skewed right with that mean and that standard deviation. Well, we know that our sample means will be normally distributed despite the fact that that's skewed right, as long as we take a sufficiently large sample, usually at least 30. So our sample means will be distributed approximately normally with the mean of the population and the standard deviation found like so. So if we want to find the probability that the mean from a sample of 40 is going to exceed 110, then we draw our normal distribution. We calculate the z-score. We should be comfortable with that. We get a z-score of 0.79, meaning we are 0.79 standard deviations to the right of the mean. On AP, if it's free response, we want to show on what side of that z-score we're finding the probability or the area under the curve. But even though we're showing this work, the nerd says go ahead and use the normal CDF and plug in the numbers either with the z-scores or like I did here with the actual mean and standard deviation of the population itself. By the way, I know it's stereotypical to put a kid down with glasses on. It makes him look more intelligent. I don't necessarily make anything of that other than the fact that I do have glasses on in order to help me look more intelligent, but that's beside the point. We're moving to the next screen, and here it is. Suppose a student claims that the mean is less than 100. They say, come on, we don't spend that much time doing social media, so we're going to test that claim. So we're going to take a random sample of 40. Now from that sample, we got a mean of 86.3 and a standard deviation of 74.4, and because that information came, those numbers came from the sample, those are statistics, not population parameters. We're doing a test on the population parameter. So that's x bar, that's S, and because it's S, we're going to use a t-distribution. The null is going to be that the mean is equal to 100 because the student is claiming that the true mean is less than 100. We took our sample, we got our sample mean here. We're going to calculate the area under the curve using those ideas of probability that we did before. Same thing we find in this case a t-score, which says how many standard errors to the left of the mean we are, not how many standard deviations to the left we are, and we get our p-value. And we can get the p-value and this t-score by doing the t-test on our calculators and then just writing those numbers in. Now, you can go watch the video on p-value and proving statistical significance to get a better feel for what the p-value is and how we can use it to reach conclusions in any type of a test. For now, suffice it to say that what we're doing here, this is a conditional probability. When you're calculating the p-value, you are saying, hey, what's the probability that we would get a result at least as extreme as the one we got, given that the null is true? So we assume that the null is true. We find, if that's the case, how often should we get a sample result at least as extreme as the one we got? Well, we estimate that it happens about 12.5% of the time. That's about 1/8. That means 1 out of every 8 samples we take, we would get a result just due to chance of that or even less if the null was really true. So what that p-value is telling us is we didn't really get that unusual of a result. So there's no reason to be doubting the null. There's not enough evidence to suggest that the alternative is true. So we would fail to reject the null in this case. If we're going to build a confidence interval for the time adults under the age of 40 spend on social media, that will be the parameter that we're going to estimate. The unknown mean of an entire population, we're not going to know that mean. We'd have to take a census, a sample of everybody, every adult under age 40, ain't going to happen. So in statistics, we use our statistics, our sample mean, to estimate this parameter. That's what we're doing with the confidence interval. We are estimating the parameter. We're not testing a claim like we did in the previous problem. So again, we got our sample this time of size 50. There's our mean, there's our standard deviation. So we proceed. Again, here's our information here. We're going to find the standard error of the sample means, how much spread we can get. The big idea here, and this is really important because students get a bit confused, when you're doing a confidence interval, you should put your unknown parameter in the middle of the sampling distribution. So what we talk about in class is we don't know what our true mean is, but we know where it is. It's in the middle of this theoretical sampling distribution. And we can know, based on the degrees of freedom, which would be 49 in this case, we can know that where we would find the middle 90% of our sample means if we took many, many samples one after another. And where we find that, we can use inverse T on our calculator or our T distribution table. But we find a critical T-score of 1.68 would trap 5% on each tail. So you look under 49 degrees of freedom or go inverse T on the calculator and you find, hey, what T-score would trap 5% on each tail? So that becomes our margin of error. We go over 1.68 standard errors in each direction. That's where we're going to trap the middle 90% of our sample means. On the next screen, in fact, let's go to the next screen. Here's the big idea. There is our margin of error. So think this through. If we were to get a sample mean right here, there's a 90% chance that any sample mean is going to be within that many standard errors of the true mean. So that's the idea behind the confidence interval. If we take that margin of error, that 1.68 standard deviations, or standard errors rather, and we add that much and we subtract that much, then we're 90% confident that we're trapping the true mean somewhere in that interval. Likewise, if, unbeknownst to us, we don't know where the sample mean is going to be, but suppose we got a sample mean down here. Again, 90% of all sample means should be within the margin of error of the true parameter. So if that was our sample mean, we wouldn't know which direction we'd find our true mean at, but we know that if we add that margin of error and subtract that margin of error, then we're probably trapping the true mean in there. The only time we wouldn't trap the true mean in our particular confidence interval is if we were unlucky enough to get a really unusually high or low sample mean, so that after we, I'll use blue this time, after we added the margin of error and subtracted the margin of error, we wouldn't quite get to trapping the true mean, because in 5% of samples, we're going to get means that are too far to the right, and in another 5% of samples, we're going to get means that are too far to the left. So even after we add and subtract the margin of error, we're not going to trap the true parameter in there. Some students picture this where whatever they got with their sample mean, if they got like 86.3 or whatever, if that was their sample mean, they tend to want to put it in the middle of the sampling distribution and visualize that the margin of error goes this way and that that's the confidence interval that they're building. That's garbage. That's a misunderstanding, and it's going to show up, if no other place, in the multiple choice section of the AP test, which is going to test to ascertain as to whether we really understand what's happening with these confidence intervals and these margins of error. So please, the unknown mean goes there, and the whole idea is we know that 90% of all sample means are within a certain margin of error, number of standard errors above and below the true mean. So by adding and subtracting that margin of error in 90% of all of our samples, we should be trapping the true mean in there. And that will help you, again, answer the tougher questions on the multiple choice, which say interpret what this means to be 90% confident. So going back here, we finish up the problem. We show all of our work. The formula sheet that's given to you on the AP exam is an awesome resource. It tells you take your statistic, plus or minus critical value, times the standard deviation of the statistic. If you can understand what parameter we're estimating, it's a population mean, then you know that your statistic is a sample mean, and all the other information is going to be contained for you on that formula page. It'll even tell you what your standard deviation is. for one sample mean, you just have to make sure you're putting an S instead of sigma because that's what you get. So show your work. This is all you really have to show. Just wrote that up there to give us the visual context of what we're supposed to put in there. So show this as your work, write down the confidence interval, and then be ready to interpret it. We are 90% confident that the true mean time that adults under age 40 spend with social media, somewhere between 37.1 minutes per day and 58.9 minutes per day. So finally, the assumptions, the conditions that have to be met is when we're doing inference on one mean, got to make sure the data comes from an SRS and respond to it. Say, we were told it was random, sample of whatever. Normality, 3 ways to check for this. If the sample size is big enough, usually at least 30, then we can assume, due to the central limit theorem, that the sampling distribution of means will be at least approximately normally distributed. I put an asterisk here because with t-distributions, the t-test is a robust test, or a robust distribution that can overcome violations of normality and still give you pretty good estimates in terms of probability for the likelihood of getting a certain sample mean. So typically we say, as long as you have a sample of at least 15, provided there's not really strong skewness or outliers, we should be fine. So be in the habit of telling the reader, hey, you know what, even if it's a little bit questionable with regards to normality, the t-test or the t-interval, those distributions are robust, they can overcome a violation of normality. That's one way to check for it. The other way is the population normal to begin with? If you're told that, then it doesn't matter what the sample size is, your sampling distribution of means is going to be normal. If neither of these two apply, small sample size, you're not told this, you should be making a stem plot or a dot plot, because the idea behind this is, if your sample data is bell-shaped, then it stands to reason that it came from a population which is bell-shaped. That's the purpose behind making a dot plot or a stem plot and saying, hey, no reason to doubt normality, we have fairly symmetric data, we're good to go. The last thing is sigma's not known, it's why we're using S and we're using a t-distribution and not a z, not a normal distribution. So the last idea is this: confidence intervals and significance tests. These are the items that you need to make sure you include with your write-up. Name it, meaning name the confidence interval or name the significance test. This is a t-test for means or a 90% confidence interval for means. I have my students state the parameter right from the front, right from the start. If you want to wait and make sure you stay the parameter that we're dealing with, the mean time that adults under 40 are spending on social media per day, make sure you state that somewhere. Address the assumptions or conditions that must be met for you to trust your results. That's on both the confidence interval and the hypothesis test. Make sure you list both hypotheses. Make sure you show ample work. Take the time to look at the example questions, the previous questions that have been given on AP, and see what the scoring looks like so that you know what's required of you with regard to how much work you need to show on a problem. And then make sure you state your conclusion. You don't just say reject the null. You don't just say we're 95% confident that this is true. You want to state things specific to the parameter that you're doing inference on. And this, again, we go back to the formula sheets that we have on AP. These are good as gold. This sheet right here is the one you want to keep referring to for inference. It will give you your basic formulas for your test statistic and for your confidence interval. So if you understand your parameter mu and your sample statistic x bar, then this is gold. You take x bar minus mu, you divide it by the standard deviation of the statistic, which is actually the standard error of the statistic. Likewise with the confidence interval, you're estimating mu, the population mean. So it's your sample mean that's statistic plus or minus critical t-score multiplied by, again, the standard deviation or the standard error of the statistics. So that is golden, and the standard deviation formulas are all down here further down the page. I believe that's it. So good luck with inference on means.